Welcome to this section on machine learning and data science applications. In this part, we'll connect some of the main ideas we discussed earlier about how NumPy works and see how they fit into machine learning pipelines, such as those in scikit-learn. Let's begin. Machine learning models, first of all, expect data to be in a two-dimensional array, even if you only have a one-dimensional array. This is important to understand. Libraries like scikit-learn expect the input data, usually called x, to have two dimensions, one for the number of samples and one for the number of features. For example, in linear regression, we often use the reshape method with -1 and 1 to turn a one-dimensional array of length 12 into a two-dimensional array with 12 rows and one column. If we try to fit a model using a one-dimensional array, we'll get an error saying that a two-dimensional array was expected, but a one-dimensional array was provided. Once we apply reshape -1, it works correctly. The reason for this is that machine learning models need multiple samples or rows, even if each sample only has one feature. That's why the two-dimensional format makes sense. So, looking back at our original array of 12 values, that's one-dimensional. Reshaping it gives us a proper two-dimensional structure that machine learning can handle. There are also times in machine learning, especially in regression, when you'll want to remove or handle outliers. Outliers can cause major issues in modeling. Sometimes they appear because of data entry errors. Other times, they might be valid points, but they distort the overall pattern of the data. For example, if your data typically follows a normal distribution and a few extreme values appear, they can pull the distribution away from normality. In such cases, you might want to clip those values. NumPy has a function for this called np.clip. It allows you to limit values within a specific range. For example, you can clip all values to be between 10 and 100. Anything below 10 becomes 10, and anything above 100 becomes 100. The same can be done for any range, such as 1 to 5 or 500 to 1000. This keeps your data within reasonable limits and reduces the influence of extreme values. Now, there's an ongoing debate about how to handle outliers. Some people argue that data should be left untouched because it reflects reality. If the data came in that way, it should be analyzed as it is. Others believe that certain extreme points should be removed or adjusted because they can distort results, especially if you've seen similar datasets before and know what's typical. Ultimately, how you handle outliers depends on the context of your analysis and the assumptions you've made. It's important to be transparent about those assumptions when presenting your findings. Another useful application of np.clip is gradient clipping in deep learning. In neural networks, gradients can sometimes explode during backpropagation, leading to instability during training. Gradient clipping helps prevent this by limiting gradient values to a specific range, such as from -5 to 5, instead of allowing them to grow excessively large, like 10 to 50. If you're familiar with partial derivatives, you know that excessively large gradients can disrupt the learning process. So, in both data preprocessing and neural network training, np.clip is a simple yet powerful tool for keeping values under control and maintaining model stability. Restricting values within a particular range is very useful. Another reason this is important is for mathematical operations like logarithms, which require positive values. Dividing by very small numbers can cause instability, so we can clip values to keep them within a specific range. The reason for this is that the logarithm of 0 is undefined, and we do not want to take the log of 0 in our computations. I've seen this happen in long-running programs where you loop through a model or a machine learning pipeline, take the difference between two values, and then attempt to apply a log transform to normalize the data. If that difference happens to be 0, the log function will throw an error and the process stops. To prevent this type of instability, it's best to clip your values so that none are too small or 0. You can see that taking the log of a -1 results in an undefined value, and taking the log of 0 returns -infinity. So running into situations like these can easily break your code. However, if you clip your values beforehand, you can avoid these issues entirely. When tuning a machine learning model, you'll often need to find optimal parameters to prevent underfitting or overfitting. The goal is to identify the best model that generalizes well to unseen data. To do this, you usually test your model with multiple sets of parameters that control things like coefficients or regularization terms. This is where np.linspace, which we've seen before, becomes very helpful. For example, when tuning a ridge regression model, you might use np.linspace to generate a range of possible alpha values. After running a grid search cross validation, you may find that the best alpha is 0.01, which provides the highest cross-validation score. This shows how np.linspace allows you to explore a wide range of parameters efficiently and identify the best configuration through brute force testing. Now, let's move to np.allclose, which is very useful in iterative optimization methods like gradient descent. Suppose we're working with a function that depends on parameters theta 0 and theta 1, such as x times theta plus theta 0 plus theta 1. We set a convergence threshold and a learning rate, much like what's done in neural networks. In each iteration, we update our parameters using the rule nu theta equals theta minus the learning rate times the gradient values. After running through many iterations, if the difference between the new theta and the previous theta becomes very small, close to 0 or within the relaxation tolerance, then the algorithm has converged. For example, in one run, the algorithm converged after 535 iterations with final parameters approximately 2.89 and 0.33. The key idea is that convergence means the model has found stable parameters that minimize the loss function. The np.allclose function helps detect this convergence by comparing whether the new and old parameter values are close enough within a defined tolerance. This is extremely useful for building machine learning algorithms where convergence is required to stop training at the right point. That wraps up this section of the course. I hope you've learned a lot and seen how powerful NumPy can be when combined with other Python libraries such as scikit, learn, matplotlib, and pandas. NumPy truly forms the foundation of modern data science and machine learning workflows.